Hello everyone, in this video we are just going to convert analog signals into digital format by using the inbuilt ADC module or ADC peripheral of the microcontroller STM32F446RE. So this particular microcontroller has a 12-bit ADC peripheral available in it, so that we can utilize that particular ADC module for converting and interfacing any kind of analog sensors to this microcontroller. In this particular video, you are just going to learn to interface any analog output type sensor to this microcontroller. Let's get started. To get the thing started, I am just going to open the Keil Microvision IDE and I am going to configure the project for the microcontroller STM32F446RE. I am just opening the Keil Microvision IDE 5. You can see there is nothing in this IDE currently open. Just click on this project tab on the top and then click on the new microvision project and go to the place where you want to store the project files. So I am just creating a folder and I am going to save the project here to be with some file name. So you can give whatever name you want for your project and save in the respective location where you want your project to be located. And here in this select device tab, just type in the microcontroller name. In my case, I am just typing STM32F446RE and then click on the device right over here and click on OK. And in the next manage runtime environment tab, here we are not going to select and import any of the board support package or any of the libraries available in the Keil Microvision IDE. We are just going to import only the startup files required for the microcontroller along with the KimSys driver, which is useful for deriving the KimSys library, which is useful for building our own program from scratch to our project. So just click on the plus near the KimSys and then click on this particular core checkbox. So this will import the KimSys file required for the microcontroller that you have selected in the previous tab, and then click on the plus near the device and then click on startup checkbox right over here and then click on OK. That's it. That's all about the files that we are going to import to our project. You can see the project has been created right over here. Just right click on the source group and create the source file, that is the main source file. Just click on the add new item to source group 1 and then click on the .c file format right over here and then give a name for your file to be main, since we are creating the main.c file required for the project. You can see this is the main file that we are going to write our program, and on the left project tab you can clearly see these are the two files that has been imported for our project. One is the startup files for the microcontroller STM32F446RE and another one is the required KimSys file. So close this. This is the KimSys file, and now let us try to write down our main function which we are going to use for writing down our program. And before writing the main function, we just want to include the required header for the microcontroller. So I am just typing #include of STM32F446xx.h. So this is the particular header for the microcontroller that we are going to work on. So the microcontroller that we are going to program is the STM32F446RE, and for that relevant microcontroller we have included the header of STM32F446xx.h. And following that I am just going to write down my main function int of main, and inside the main function I am just writing the while of 1, that is the infinite loop of the embedded program. So all the embedded programs that we are developing right over here in the Keil Microvision IDE will be having two different parts. One is the major part, that is the main function, and another one is the infinite loop of the program, which will be containing the set of instructions that needs to be executed again and again until the microcontroller is stopped. This particular infinite loop will hold the logical set of instructions which needs to be executed again and again until the microcontroller is stopped. And before the while of 1 we have the main function, and before while of 1 is the part where we will be writing the set of instructions that needs to be executed only once in the lifetime of the program. Before while of 1 we will be using the main function for configuration segment of the program, which will be executed only once in the lifetime of the program, and inside the while of 1 we will be writing the logical set of instructions that needs to be executed again and again until the microcontroller is stopped. So let's move to the main program that we want to develop in this particular video. So in this particular video we are just going to configure the ADC peripheral of the microcontroller STM32F4 for converting an analog voltage signal given at a particular ADC channel of the microcontroller. So this is what we are going to do. For that, the first thing that we want to find out is what are all the ADC modules or peripherals available in the microcontroller, and we have to choose the ADC channel in which we are going to perform the conversion. So there will be several ADC modules or several ADC peripherals in the microcontroller, and we are just going to choose one among them, and in that particular ADC peripheral we are just going to choose a particular channel in which we are just going to convert the analog signal into digital format, and after that we are just going to perform all these steps. So these are the steps required for converting the analog signals into digital format by using the ADC peripheral of the microcontroller that I have already derived. So these are the steps that we are going to perform, and before that we just want to analyze what are all the ADC modules available in the microcontroller, and following that we are just going to choose a ADC channel in which we are going to perform the conversion. So I am just opening the user manual of the microcontroller. So I have opened the datasheet and also the user manual of the microcontroller that I am working on, and here you can clearly see. So here you can see from the user manual we have 3 different ADC modules: ADC1, ADC2 and ADC3. So we can use any one of these 3 ADC modules for converting an analog signal to digital format in our microcontroller. So we can configure any one. We need not configure all the 3. We are just going to configure one particular ADC channel for the conversion. So I am just going to select the ADC channel 1. So here in our program, now I have chosen this to be ADC 1. So we have totally 3 different ADC modules available in the microcontroller, and among them we have chosen ADC 1. And now it's time for the channel that we want to work on. So channel is nothing but the analog pin of the microcontroller in which we want to perform the analog to digital conversion. So for finding that, or for finding the available channels for the required ADC module, you can open the datasheet and move to the alternate functions table right over here. I'm just zooming in a bit, and here you can see a STM32F446XX pin and ball description. So in this particular table you can find all the possible alternate functions along with the additional functionalities for each pin of the microcontroller. For example, I'm just scrolling down a bit, you can clearly see. I'm just taking one example. You can clearly see here we have PF3 pin, and this pin can be used as alternate functions of FMC-A3 and event out, and following that it has an additional function of ADC3 IN9, meaning that this particular PF3 can be configured as ADC3 channel 9. So input 9 is nothing but channel input 9. So similarly we are just going to choose the ADC channel for the ADC1 module. So let me come to this directly. So I'm just going to choose the PA0 pin. So PA0 pin is nothing but it can be used as timer 2 channel 1, timer 5 channel 1, timer 8 ETR, timer 2 ETR, USR2 CETS, UART 4 TX, event out, etc. And following that, this particular PA0 can also be configured as ADC1 channel 0, ADC2 channel 0, ADC3 channel 0, that is given as ADC123 underscore IN0. So if it is given as ADC123, it is having the meaning like it can be configured in ADC1 module, ADC2 module, and also in ADC3 module. So we are just going to configure this particular channel as ADC1 channel 0. So here we have chosen the channel to be PA0. That's it. Now moving to the configuration of ADC module. The first and foremost step that we are going to do is we are just going to enable the internal oscillator. This step is optional. If you have already enabled the internal oscillator, or by default the internal oscillator of 16 MHz will be enabled in the Nucleo F446RE development board, so you need not do this, but for safety reasons you can perform this. You just want to enable the bit number 0 in control register of RCC. So we have been doing this for a while in all the previous videos, so I hope I don't need to explain this to you again. And the next step is I just want to enable the port clock of ADC channel selected. So we have selected the channel to be PA0, so we need to enable the GPIO A clock. Since we are going to configure the PA0 as analog pin, we just want to enable the clock of GPIO A, and then we want to enable the clock of ADC peripheral, and we want to move on. So first step is we just want to enable the port clock of PA0, that is nothing but we want to enable the GPIO A clock. As we did before, the shortcut for finding the bus to which the peripheral of the microcontroller is connected, just open the block diagram in the data sheet by moving to the page number 16, and here in this block diagram you can see here clearly, here is the GPIO port A, and this is connected directly to AHB1 bus of the microcontroller. So for enabling the clock of this particular GPIO A peripheral, you just want to go to the AHB1 ENR register, and for disabling the clock you just want to move to AHB1 RSTR register in the RCC peripheral of the user manual. So I'm just moving to the reset and clock control chapter in the user manual, and in the registers section just go to the register directly, that is the register of AHP1 ENR. So where is it? Here is it. You can see here is the AHP1 ENR, and as we found out, GPIO A is connected to AHP1 ENR from the block diagram. You can clearly see here is the GPIO A enable bit, that is the bit number 0 of the register. So for enabling the clock of GPIO A, I just want to set 1 to this bit number 0 of the register. So here I'm just going to use the same pointer RCC, and I'm going to point to AHB1 ENR, and I'm going to set to the bit number 0 for enabling the clock of GPIO A. And then the next step is we just want to select the analog function mode for the analog pin PA0. So we have selected the channel for conversion to be PA0, so we want to set the mode of the PA0 pin to be analog mode. So for that, move to the GPIO chapter of the user manual. Here in the registers tab, go to the mode or register, and in this register you can clearly see we have two bits assigned for a particular pin, meaning like bit number 0 and 1 combined together is useful for configuring PA0, and it goes on like this. And we have chosen the channel to be PA0. So these two particular bit number 0 and bit number 1 will be helpful for configuring the PA0 of the microcontroller. So we want the PA0 to be configured in analog mode. So we want to set 1 to both of these bits for configuring the PA0 in analog mode. So here you can clearly see 1 1 in both the bits will configure the particular channel in analog mode. So let's do that. So now what we want to do is we just want to use the pointer of GPIOA and move to the mode R register, and I am setting the bit number 0 and again I am using the same mode R register, and I am going to set to the bit number 1. So these two lines will configure the PA0 in analog mode. And the next step is we will enable the clock of the ADC, that is ADC1. So this can be done by using the same reset and control registers. Go to the block diagram again, and now I just want to find where is the ADC1 peripheral. You can clearly see here is the ADC1 and it is connected to the APB2 bus of the microcontroller. So I just want to move to the APB2 ENR register in the reset and clock control chapter of the user manual, and I want to enable the ADC1 clock. And from this register you can clearly see the bit number 8 right over here is useful for enabling the clock of ADC1. So I am just enabling the clock of ADC1 by enabling the bit number 1 or by writing 1 to the bit number 8. So this time I am just using the RCC pointer for configuring the APB2 ENR, and I am going to set the bit number 8. And following that, here I just want to turn off the ADC1 sequence. I just want to start the sequence here, and I want to set the number of channels for which the conversion needs to be done, and following that I will enable the ADC again. So before configuring these two things, I just want to turn off the ADC. I just want to make sure that the ADC is turned off. So ADC1. So this can be done by moving to the chapter of ADC analog to digital converter in the user manual, and in the registers of control register 2. So this is the ADC control register 2 in our microcontroller, and in this particular register the bit number 0 is AD on, which is useful for turning on the ADC. So here I am just moving to that particular bit. You can see here bit number 0 in this register is nothing but AD converter on or off. Writing 1 to this particular bit will enable the ADC, and writing 0 will disable the ADC. So I am just going to perform the same. Here I am just going to use the ADC1 pointer CR2, and I am going to disable the ADC. I have turned off the ADC here, and here I am just going to turn on the ADC, the same bit. And in this particular conversion sequence start, I am just going to show you what sequence needs to be started here. So move to the sequence registers in the ADC chapter in the user manual. So for all the ADC channels that you are configuring, you just want to define a sequence. So in our case, we have 15 or 16 sequences. Clearly you can see we have ADC SQR3 register, and in this particular register we have SQ1, SQ2, 3, 4, 5, 6, and in the ADC SQR2 register we have SQ7, 8, 9, 10, 11, 12, and in SQR1 we have SQ13, 14, 15 and 16. So you can define any one particular sequence for the conversion that you are making. So I am just going to use the SQ1 sequence right over here. So I am just setting the bit number 0 right over here. So if you want to use the sequence of SQ2, you just want to set the bit number 5 in this particular register. So here I am just going to set to the SQ3 bit number 0, and following that we just want to set the number of conversions that you want to make. So that is already available in the SQ1 register right over here. You can clearly see the bit numbers from 23 to 20 will define the length of the conversion that you are making. So if you are configuring two different channels, you can write 1 to it, and if you want only one conversion to happen right over here, you can just write 0 to this particular 4 bits from 20th bit to 23rd bit of the particular SQR1 register. You can clearly see the L bits right over here. 23 to 20 will define the number of conversions. 0000 will configure only one channel or one conversion. 0001 will configure 2 channel, and 1111 will configure 16 conversions. That's it. So here I am just SQR1, I am just going to write directly 00 to all the bits. And that's all about the configuration lines that you want to do for configuring the ADC module of the microcontroller for one particular channel. And these 3 statements must be implemented inside the while of 1, that is inside the infinite loop. Start the conversion, you just want to write 1 to the start bit of the ADC. So that is available in the same control register of ADC. So same CR2 register, you can see the bit number 30, that is this particular bit is useful for starting the ADC conversion. So I'm going to the bit number 30. You can clearly see writing 1 starts the conversion of regular channels. The bit can be set only when AD on is 1, otherwise no conversion is launched. So we have already turned on the AD on right over here. So here I am just going to start the conversion, CR2, start the conversion, and I am going to wait here until the conversion is complete. So we have a particular flag for monitoring whether the ADC conversion is complete. So that flag can be seen in the ADC status register. This is the ADC status register, and in this status register the bit number 1 is EOC bit, which is useful for identifying the end of conversion. So during the regular conversion of channels, once the ADC conversion is complete, this particular flag will be raised by the microcontroller. So we will be monitoring until the flag is set, that is until the bit 1 in this particular register is high, and we will read the ADC data register. So we will be monitoring this particular bit by using a while loop, and finally we will be reading the ADC data register, that is DR register, for fetching the equivalent digital 12-bit value for the analog voltage provided at the PA0 channel. So this is showing an error because the ADC data is not defined. So I am just defining this particular ADC data, declaring and defining it. Now I am just compiling the program. You can see the program is compiled with 0 errors and 0 warnings. Now I have already connected my nuclear development board to the PC through mini USB cable. I am just clicking on the options for target, debug. Here select the ST-Link debugger. You can see the ID of the microcontroller is showing right over here, which means the connection is proper. Now I am just going to dump the flash to the microcontroller. Just click on the icon right over here, or you can just click on F8 in the keyboard. The programming is successfully done, verification is done, and the flash has been loaded successfully. Now I am just moving the window to debug session. So the view will be changed from program view to debug view. Just click on the icon right over here for moving the session to debug view, and here I am just going to double click on this ADC data, right click, add ADC data to watch 1. You can see the ADC data is added to the watch window of the debug session. Right click on this and click on the hexadecimal display so that the value will be shown in the decimal format. Now I have not connected anything to the ADC PA0 pin, so our expectation is some toggling value will be displayed in the ADC data variable right over here. You can see the ADC data is having some toggling value. Sorry. Okay. Now we have one particular problem right over here. I will show you what is that problem. This PA0 is actually a wake up pin by default. So connecting the ADC, configuring this particular channel to ADC1 will not show you or read the proper voltage that you are providing to this particular pin. So what we will do is we will make a slight change in the program for changing the channel selected here to be PA1 instead of PA0. So we will be configuring the PA1 as ADC1 channel 1 instead of PA0 as ADC1 channel 0. So we will be configuring PA1 as ADC1 channel 1 instead of PA0 as ADC1 channel 0. So we will make the configuration only a bit changed. So here instead of PA0 we are just configuring PA1 in analog mode. So for that I just want to set bit number 2 and bit number 3. As you can see clearly from the GPIO chapter mode R, I just want to configure these 2 bits in analog mode for configuring PA1, not these 2 bits. So I have done this. So that's it. Other than that, you don't need to do anything. I'm just compiling the program again. And I'm moving to the download section. I'm just clicking on the icon right over here, or F8 in the keyboard for dumping the program to the microcontroller, and I'm clicking on the start debug session icon right over here. Now I'm just running the program. You can clearly see we have some random values being fetched by the microcontroller PA1 channel, that is ADC1 channel 1 of the microcontroller. So we successfully configured PA1 as ADC1 channel 1, and we read the values via that channel and we loaded the value to the ADC data. So the maximum value that we can fetch from this particular ADC data variable is 4095, that is 12-bit value, and for 3.3 volts we will be having the 4095, and 0 volts we will be having the value 0. So this is the ADC conversion that is happening right over here. So now I am connecting the PA1 pin of the microcontroller to 3.3 volt. You can see I am getting 4095, which is the maximum ADC value that can be read. And now I am just going to connect the same PA1 pin to ground of the nuclear development board. Now you can see I am getting the minimum value, that is 0 or 1, minimum step value. So when I connect again the 3.3 from the nuclear development board, we will be having 4095, which is the maximum value, and when I connect again the ground, we will be having the minimum value 0, 1, 2, 3, etc. So we successfully read the analog voltage that is given at the PA1 pin of the STM32F4 microcontroller by configuring that particular pin in ADC1 channel 1. So we configured the ADC peripheral of the microcontroller for reading the analog voltage signal, and we successfully converted that particular voltage signal into digital format, that is 12-bit digital format, in this particular video. I hope you learnt something new in this video. So using this particular technique, you can interface any kind of analog output type sensor to this particular analog channel of the microcontroller. You can configure any analog channel of the microcontroller. I have shown you only one particular channel. Similar way, you can configure any of the channel of the microcontroller for reading analog voltage signal from analog output type sensors. See you in the next video. Thanks for watching.